So hi guys, this number of meetups about concurrency topic in .NET, which is very important topic in order to create robust and scalable applications. First couple of notes about the structure of these meetups. Today is just an introductory meetup about the concurrency as a concept. Uh, then tomorrow and on Wednesday, we'll cover tasks and async await construction, which is a building block for everything else. And later on Friday and next week, we'll discuss thread synchronization concepts, thread safe collections, and advanced performance tips, etc. So without further ado, let's dive into it. What is concurrency? Let me just share my screen. I don't really have anything to present for now because I'll just talk about concurrency, but anyway. Concurrency is doing more than one thing at a time, in essence. So this can be achieved in multiple ways. It's not necessarily a parallel execution of something. It can be a sequential execution. But if we are doing at least two things at the same time, it's called concurrency. Why do we need it? Historically, in the past, operation systems were single-threaded. So whenever, for example, you sent a document on a printer to print, the whole machine froze until it was printed. So essentially, operation systems introduced the concept of concurrency in order to handle multiple operations executing at the same time. For instance, if I move a cursor here, operation system draws a new position of the cursor, even though I have other applications that are executing in the background. So for that, Windows have first of all, Windows have operation system has different processes, same as Linux. Every process is isolated in memory, and every process can have a number of threads that can also execute concurrently with each other. How does it work? First, one more note about why do we need it? Why do we need concurrency? First use case is GUI applications. When we have a GUI application, we don't want it to hang. We want it to be responsive. So if, for example, my application needs to download a file from internet, we want to have some progress bar. We want to be able to interact with application. We don't want the whole UI to freeze. So we need at least one thread running the GUI application and another thread downloading our file. Second use case are servers. So when we have server applications, web APIs, etc., we want to execute every request in parallel with every other request. Because imagine if 10,000 users send a request to our web server, and our web server can process only one at a time, and every request takes like a second. So then the latest user will wait for quite a bit in order to get his request processed. This is why we want our requests to be processed in parallel always. How does it work? In the past, and not so distant past, to be honest, all CPUs were pretty much single core. So single core CPU, it cannot process any operations in parallel. It can only process instructions one by one sequentially. So how does this kind of CPU achieve concurrency? Let's imagine I have a good analog here. Let's imagine that our CPU needs to peel bananas. And in order to peel one banana, it needs to do 3 peel operations. Each operation takes 1 second. So in order to peel one banana, it needs 3 seconds in total. However, if we want to peel 2 bananas, our single core CPU can only do it sequentially. So it can peel one banana, then it can peel another banana. The user that scheduled peeling of a green banana will be outraged, to be honest, because this banana wasn't peeled in 3 seconds. It was peeled in 6 seconds because this user was waiting first for the user that scheduled yellow banana to be peeled. So in order to create at least a visibility of peeling the same bananas at the same time, operation systems introduced the concept of context switching. What does it mean? It means that our operation is split into small chunks, and every chunk is processed. For example, we peel only one banana one time. Then CPU switches to another banana and peels it also one time. Then it switches back. So this time, both green banana user and yellow banana user, they both see their bananas being peeled. Sure, they peeled for 6 seconds both, and it takes a lot of time, but at least now they are peeled concurrently. Unfortunately, this process has its drawbacks. This context switching, it also takes time because CPU needs to put one banana on the table, then take another one from the table, and only then it can continue peeling them. In technical terms, CPU has cache and registers and different information that it gets from memory. And whenever operation system switches threads, this information needs to be cached somewhere. It needs to be overwritten by some different information for another thread, and only then that different thread needs to can continue executing. So context switching comes with overhead, and we need to avoid it if we can. Ideally, we never want to have context switching happening. So this process of peeling one banana and another banana, even though context switching is happening, operation system is calling the thread. This is the concept of a thread. Thread is a concept of operation system that allows us to abstract away from all these context switches and just observe a single operation status. So we can see, for example, the thread 1 is peeling a yellow banana, and thread 2 is peeling green banana. Now, how do multi-core CPU work? In multi-core CPUs, there are multiple cores. It's almost the same as if they would be completely different separate CPUs. So each core has its own memory registers that can be filled with different data, and it has its own calculation chip that is able to run instructions. So what it means that every core can process operations completely in parallel with other cores. So returning to previous example, we can now just give one core a green banana and another core a yellow banana, and they will peel them both in 3 seconds without any context switches. One more note about how hyper-threading works. Also, hyper-threading is a technology patented by Intel, and it creates logical. It has, for example, if your CPU has 8 cores, then it will have 16 logical cores. So CPU reports to the system that the amount of cores that it has is 16, not 8. So the amount of logical cores. And the operation system schedules all the work as if there would be 16 physical cores on the CPU. However, some kind of context switching is still happening there. In fact, in hyper-threaded CPU, there are 8 cores, not 16. However, every hyper-threaded core has 2 memory storage units. So not one, but two, but only one calculation unit. So when one core of that hyper-threaded CPU wants to build two bananas, it can store both states of those both bananas in its internal storage because it has two different storages. And then it just builds one banana, then another, then first one, then second again, but it doesn't need to clear and to override this data storage because every CPU has two of them, so there is less overhead. Basically, we can remove all the switches here. It's like if they are not happening at all. CPU can just build them all without switching between them. So operation system introduced these concepts, threads. However, threads are very expensive to create. So when you create a thread, it takes a lot of memory, first of all. It uses quite a bit of CPU resources to create it. And also it will use quite a bit to destroy it. So we want to avoid creating threads as much as possible. We don't want to create them manually. Actually, Stephen Cleary once told that as soon as you have this code, this type of code in your code, it's over. Your project already has legacy code. So nobody uses that nowadays, unless you really need a new thread. These constructions, I won't even cover it in this number of meetups, but it creates a new thread, new operation system thread. So it will impact performance, it will use memory, and it will create completely new thread. You don't want to do that because .NET provides for you a thread pool, which already has all the threads created. I'll get to it a bit later. First, before delving into .NET specifics and thread pool, I wanted to discuss CPU bound work and IO bound work. Many of you heard those concepts. Probably you all know what it is, but I just wanted to touch it here again. CPU bound work is work that needs to be executed on the CPU. For example, peeling of bananas. So one CPU can peel 100 bananas as fast as it can, and it will use it will be used to 100%. So whenever you have CPU bound work, you can split it between the number of cores that your CPU has, and then your CPU will be 100% loaded for that work. It can be work for sorting arrays, for moving data between different memory locations, to calculate something, etc. You do not want to schedule CPU-bound work to more threads than you have cores, because then context switching will occur and you will not be able to process it faster anyway. You will build both bananas in more than 6 seconds, not even 6 seconds, because all the context switches will occur. So in order to process CPU-bound work as fast as possible, you need to make sure there is no context switching. You need to make sure that you only schedule it to the same amount of threads that you have physical cores on your CPU. IO-bound work is input-output work. It's work that is waiting for some other device or some other data, for example, network data. The difference with IO work is that CPU doesn't do anything while it's waiting, obviously. So in terms of this example, imagine that you need to also, after peeling a banana, you need to fill a bottle of water from the sink tap. And after peeling a banana, you place a bottle in the sink, you wait for 3 seconds, and it's completely filled. However, you're not pouring water yourself. The sink tap doing that for you. You're just waiting for the bottle to be filled. So how can we optimize this? We can do this. We can put a bottle into the sink, then we can peel our banana using CPU for 100% while peeling it. And then we can just take the bottle from the sink because it will be filled by that sink tap. We actually can even place 1000 bottles into the sink and fill them all at the same time because it's I/O bound work. Our CPU doesn't need to do anything at all. However, there is different consideration to think about when scheduling I/O bound work. Obviously, that's throughput. So in this case, our sink tap is some different I/O device. For example, hard disk drive from which we are copying files into our system. And it has some throughput. For example, imagine that our sink tap can fill 3 bottles of water in 3 seconds. However, imagine that we have a very little streak of water running from our sink tap, so our throughput is limited. We can either fill 1 bottle of water in 3 seconds, or we can place all 3 bottles of water into the sink, but they all 3 will be filled only by 1/3 in those 3 seconds. So we will need to wait for 9 seconds in order for them all to be filled. This is always a consideration. So for example, if our database can serve files only with 10 megabytes per second, but your overall network can provide you 200 megabytes per second, you still cannot schedule work and expect it to be downloaded in 200 megabytes per second speed because database is limiting our speed, or vice versa. If you have a narrow network channel, but database can serve huge amounts of data, you obviously are limited by the network channel. Now, as I told, thread creation is very expensive operation. I'll just highlight it here again. It's just not that it uses more memory and CPU. It also every thread needs to be paused and resumed every time garbage collection occurs. So whenever we have application and garbage collection occurs from time to time, imagine if your application has 1000 threads, all 1000 of them needs to be paused. Then application waits for them to be paused. Then after they post, garbage collection needs to go through all of the thread stacks as well to gather data from all the threads. Then it marks all the objects for collection and collects them if needed, and then it resumes all the threads. This is why we also want to limit the total amount of threads that we have, if possible. Same thing also happens in Visual Studio, by the way, because every time we pause in debugger, Visual Studio needs to pause all the threads. So if your debugging experience in Visual Studio is laggy or slow, it might just be that it's not that you have slow machine, but it's that the project creates a ton of threads and Visual Studio starts to lag behind. So now, yeah, let's finally see some examples in .NET. So .NET has a ThreadPool. ThreadPool is an abstraction for threads. It's a pool of threads that are created on application startup for you to use. So for example, when you start application, let's say 20 threads are created initially. And whenever you schedule some work using specific methods of .NET like task run, which you probably should use in 99% of the cases, then this work is scheduled to be executed on some free thread of the thread pool. After this work is executed, this thread that was executing it returned to thread pool and can be reused by any other tasks or work. default number of threads that is created in ThreadPool is amount of cores in the CPU, because we want to avoid creating more than them, obviously, because our CPU won't be able to handle them without context switching. So this is why default number of threads is the amount of cores. However, this was actually the case for all .NET. In the latest .NET Core, ThreadPool has been optimized a lot. So now it aggressively deletes all unnecessary threads from ThreadPool, and it recreates it on demand up to the amount of your physical CPU cores. So let me just show you it in example. Let me run this example. So here we'll wait for 1 hour. It just blocks main thread. Thread sleep just blocks current thread, so it will block main thread and wait for 1 hour. If I pause this application, we can see in threads window all the threads of this application. Ignore these 4 threads. That's some .NET or Visual Studio threads that we are not interested in. We are interested in main thread and any thread that is named .NET TP worker. .NET TP worker is a worker thread of ThreadPool that was created for us to use. These threads, as you can see, there are only 4 of them, even though my machine has 16 cores. This is one optimization of .NET Core. It doesn't create as much threads initially. Furthermore, if I run application again and I pause it again, you can see that they already disappeared. This is because ThreadPool saw that we are not using any threads right now for some time, and it deleted them. So now we only have main thread. Not a single ThreadPool thread is currently exists. So yeah, a couple more words about Visual Studio debugging. Visual Studio allows us to see a lot of cool stuff here. In threads window, you can mark current threads that are used by your own code by clicking flag just my code. Then we'll see that there is only one thread currently that's executing our code. It's main thread. All the other threads are executing some other code. For example, these 4 worker threads, they're executing some method get completion status. It basically means that they are all doing nothing. They're just waiting for some work to be scheduled on them, and then they will pick it up and start processing it. There is also a call stack that shows for a specific thread what is actually being called. So in this case, we are calling method main. And there is a parallel stacks window. This is a very cool window. I'll talk about it a bit later, but it shows graphical representation of our call stacks in different threads. So yeah, I told previously that .NET ThreadPool creates threads on demand up to a number of physical CPU cores. What does it mean? Does it mean that we cannot create more threads than cores? Well, ThreadPool has a smart debounce in order to not create more threads than needed. It's a debounce for half a second to create every other thread after the limit has been reached. So in case of 16-core CPU, I can write 16 times task run and block a thread inside, thread sleep 1 hour or something. I can write this 16 times and 16 threads will be created and they will all be blocked instantly. However, if I write it 17 times, 17th thread will only be created with a half a second pause. So every other thread will wait for half a second before it is created. This is done in order to reuse already existing threads. So if your operation returns earlier than half a second and all threads are occupied currently, and your some operation returns earlier than half a second, then it will just be used for your operation instead of creating a new thread. This is a very cool feature. We'll talk about how not to block threads in order to use that functionality. So thread sleep operation is very bad. Never use it. It blocks the thread, and if you do it, for example, for all the threads will be blocked, and new ones will need to be created, waiting that half a second pause. Now let's look at the means to create a work and delegate it on some other thread. As I told, the best way to create a new work is task run. You should use it in 99% of the cases, but here I'll start from this method. Queue user work item. ThreadPool queue user work item, it works almost the same as task run. It delegates this work to be executed by some free thread of ThreadPool at a time when this thread will be free. So it doesn't guarantee that it will start executing instantly, although it does usually execute pretty much instantly. It will execute whenever some thread of ThreadPool can execute it. In this example, I delegate to this delegate 2 times on some other thread, and inside it just blocks the thread with thread sleep for 1 hour. Let's see what happens. Now, if I pause this application and I flag just my code, we can see that there are 3 threads marked with red flag. First one is main, which is just waiting on console read line. Then it's a 10th thread of ThreadPool, which is currently on thread sleep. So it's here. And there is 5th thread of ThreadPool, which is currently also on thread sleep. Visual debugging capabilities also allow me to switch to that thread. For example, now I switch to 5th thread. We can see that it's standing on this instruction. And on this parallel stacks window, we can even see that there are 4 threads in total. And 2 threads are currently just waiting and doing nothing. It's these ones, not from our code, just 3 threads of ThreadPool. And 2 threads from ThreadPool are currently calling method do something, which is this one. And inside is calling thread sleep. If I continue application and just pause it again, then we'll see that the other 2 will disappear. Only our remains because ThreadPool deleted unused threads again. So queue user work item, it accepts a delegate. It accepts a delegate wait callback, which accepts object state and returns void. So any method that has the same signature will be able to pass it inside and use it. I'll talk about why we need that state and how we can use it in the next week when we'll discuss advanced performance tips, because it can improve some performance if you use it correctly. But for now, it's not important. One main distinction between task run and ThreadPool queue user work item is that let's see this example. What if inside that method we throw an exception? Nothing will happen, right? Well, see, our application crashed. any work that is delegated using queue work item, if it throws an exception, it will crash the whole host. Even if you use this method from any other method or from within tasks, or if you call like task run and then you use this method inside like this, it will throw an exception anyway and crash the host. So if you are really forced to use queue work item instead of using task run, do include try catch inside of your method that is being executed by queue work item, and do not rethrow that exception. Another main distinction is that we cannot do anything with the result. We do not know when this method will finish. We do not know whether it has already finished or not. We do not have any result. We cannot cancel it. This method just returns Boolean, whether it has been scheduled or not. And it, in 99% cases, just returns true. So really, it's much better alternative to this to use task run and use tasks. Internally, tasks use this method, so that's why I'm showing it. It's a main method to schedule work on the ThreadPool. Task is an abstraction around this method. So one more topic I want to cover in this introductory meetup is execution context. What is execution context? Whenever you use queue work item method or task run method, or you use async await to await some task, .NET does two things. .NET does one thing. It saves current data, like metadata, security information, etc., some different data values associated with current thread. And it flows this data inside your delegate, which you scheduled using queue work item or task run or using await. It just flows it into the method that is being executed on a different thread. This execution context is something that just exists. You do not need to know about it really. You just can. It just exists in .NET. It's not the synchronization context. It's nothing to do with configure await instruction. It's nothing that can introduce any deadlocks or anything like that. It's just something that exists, and in 99% cases, you do not need to interfere with it. However, what does it mean for us? We can save information in this execution context in order for it to be passed into our delegate. In the past, we could write something like execution context, state bug or data or something like this, and just set some values in a dictionary style. In .NET Core, it has been removed because there is a new type, async local. Whenever you create an async local variable in, for example, in your class, this variable is stored in execution context automatically behind the scenes. So that execution context, it allows us to use async local. If there wouldn't be execution context, then we wouldn't be able to do that. And this is an example of using async local. So for example, we have some static variable, and we have async local variable. And let's say we schedule two methods on a ThreadPool, change values and do something. Let me just close the window. And do something, it change values, it instantly changes our static variable. to Peter, and it changes async local value to Peter. But to do something, it waits for 2 seconds, and then it prints to console both static name and async local name value. If you run this example, we'll see that static value is now Peter, but async local value is still Ivan. It's because when we scheduled these methods do something, this value has still been Ivan, and this value has been copied into the execution context that flew into the queue server, into the do something method. You can suppress execution context, which we'll also cover in advanced performance techniques. If we suppress flow, then execution context will be completely null and all the data will be completely lost. So in this case, async local value will just be null. It will be just nothing. It might improve performance somewhat, but the performance gains are negligible, so you really shouldn't use it any in 99% of cases again. So yeah, since we have some time, let's talk about tasks. I know tasks are planned for tomorrow, but let's just start because it's an important topic to distinguish user work item and tasks. So when we schedule some work using method task run, we also pass there a delegate. It actually accepts action, so just avoid without any parameters. And it runs it on a free thread of ThreadPool. We can throw exceptions inside it. They will not crash the host. And we can observe result. Method task run returns a new class object task, which has field status that can be in one of these states. So when task is still running, it can be in one of these states. When tasks has already finished, so your delegate has run to completion, it will be in this state if it successfully completed. It will be in this state if it is cancelled, and if it will be in this state in faulted if some exception has been thrown inside of it. A task also has a method wait, which will block current thread until the task is executed. It's also a bit easier to do this, same as thread sleep. Do not do these things. We'll discuss later how to avoid it and how to not block the thread. And tasks can be created using task factory class in order to just avoid duplication. Imagine that we need to create multiple tasks doing the same and with the same configuration. The task can accept different values like cancellation token, etc. But we want to pass the same cancellation token to all the tasks, configure them in similar manner, and execute the same method. We can just create a new task factory. And then from this new task factory, we can use a method start new, passing a delegate, and it will apply all the parameters that we passed into the task factory, like cancellation token, task scheduler, task creation options, etc., to all the tasks that are created by this task factory. Maybe somebody has any questions about what we discussed so far?
Yes, I have a question. You said, first, thanks for the lecture. You said that we should avoid creating threads manually. Instead, we should use ThreadPool.
Yeah.
But ThreadPool provides only background threads. If we need foreground threads, do we have any other option instead of creating threads manually?
Thank you for the question. It's a good question. I forgot to cover it, or it was planned for tomorrow. I don't remember, but anyway, thanks. One more note. I'll just talk about it briefly. There are two types of threads in .NET, foreground threads and background threads. And by default, when you create an application, your main thread is a foreground thread. And all the threads from ThreadPool are background threads. ThreadPool cannot have foreground threads. All of them are background, and you cannot change it. What does it mean? Well, if we write here something in console, right? It doesn't even matter that we are waiting for 1 hour in our background thread. When we hit enter in our console, you're right. It's because we blocked the main thread here. Yeah, better example. Anyway, if we have an application that just reads for console and we hit an enter here, we'll exit the main thread and the application will exit. Or if some exception is thrown, it will crash. However, the main trigger for application to stop is not exiting from the main thread. It's the trigger is that there are no foreground thread in the application anymore. So if we create a new thread using new thread construction, and we pass here configuration that it is a foreground thread, then application will not stop working even after we exit main thread. It will not stop working until all of foreground threads, wherever we created them, stop. Now, returning to the question, I am not aware of any other way to create foreground threads. Maybe there is. I didn't investigate that matter. But this thing is not like calling a new thread. It's not as bad as using GoTo or something. It's not a stigma. It is an instrument. It needs to be used whenever we need to use it. For example, when we need to create foreground threads. This is why I mentioned that in 99% of cases you shouldn't use it because you rarely need foreground threads. But whenever you need to, yeah, I think this is an appropriate way to create them.
Thank you. And another small question. In your practice, how often have you had to create foreground threads?
In my practice, never. This is why I never investigated that question.
Okay, the same for me. Thanks.
So, anybody else?
Hello. Yeah, thank you for session. Yeah, I just have a question regarding that time, like half a second time halt before creating new thread, right? Is it like estimated value or it's hard-coded somewhere? And yeah, just described in the documentation.
I think it is a hard-coded value. I don't think we can change it. I also didn't investigate it. Maybe there is a way to change it, of course. I wouldn't say that for 100%. But yeah, it is there. Like in a good application, imagine you have a server and 10,000 users calling your endpoint at the same time. Thing is that if you don't have a blocking code, if you do not block any threads at all, if all your code is async and you are never blocking a thread, then there is a high chance unless you're calculating some NASA data, that all these 10,000 threads will be processed even with less amount of threads than total amount of cores of your machine, because they will just be processed. All the threads will just be used for chunks of your async methods between awaits of different requests. This is why it's a very good practice to write non-blocking code and never write blocking code. This is why I also highlighted that never use wait, never use thread sleep. It's very bad idea to do that. I'll just highlight it again. It might seem to you that it might be a good idea to use somewhere await, or use somewhere task result, or use thread sleep, or use something blocking, anything blocking at all. For example, you have async method, but you really need it in that sync method, and you cannot change the code. So you go ahead and you block the thread. However, if there is chance that this piece of this method will be executed by more than one thread, for example, it's not a startup code of your application, but it's really an endpoint, especially if it's an endpoint that is on your hot path. So your users are calling it 100,000 times per day. Then it is no. You should never block it, because it might lead to thread starvation. It will mean that if 100 users reach that piece of your method that is blocking at the same time, at some point of time, and it takes more than half a second, then thread, first of all, even if it doesn't take more than half a second, it means that more than, if you have more requests from more users than your machine has cores, then all the rest will be just waiting for threads to become available. So it will already slow down their response time.
It increases responsiveness.
Yeah.
And by the way, is it like a part of aggressive strategy of ThreadPool, right? To avoid these causes of increasing number of threads, like more than number of cores and so on. And like, is this the part which considers like a blocking operations like thread sleep? It's also considered as like an operation to put the thread back to pool, like if it's like thread sleep, for instance, and just to make it available to process another operation there, like to get it available.
Well, that's the problem with thread sleep. That's why I say never use it. Thread sleep blocks current thread, so it will never be returned to thread pool to use it by another operation. So if we write here thread sleep for 1 hour, it will just block the thread for 1 hour. If we write 16 operations like this, it will block all 16 threads for 1 hour. So if during that hour we need to execute something else on the thread pool will wait for half a second, and only then it will create us 17th thread that will execute our operation. And after our operation is done, it will, after some time, also remove that 17th thread again, because nothing is executing on that 17th thread. And later, if we need to execute something again, it will again wait for half a second before creating it.
Okay. I was just wondering what's the aggressive thing
Yeah,
there.
the much better way, we'll discuss it tomorrow, much better way to unblock operation and is using task delay. Because task delay, it doesn't block the thread. It just creates a task that will finish, that will be transferred to completed state, that will finish execution in 1 second or if you write here 1 hour, in 1 hour. We can then save this task to a variable and check it periodically, or we can like check the status periodically, or we can use continue with to run some other delegate after it executes, or we can await it, which will also not block current thread. Await will just schedule continuation after it executes.
Yeah, it's interesting what kind of optimizations can perform under the hood within the operations. Different kind of operations.
Yeah, okay. And delay, it internally works on timers. So it doesn't, there is no thread. There is one good article from Stephen Cleary, there is no thread. There is no thread when you create a new task delay. Task, I'll just highlight it. Task is an abstraction around operation that we need to do. It's not an abstraction around the thread. There is no thread when we create task until that delegate is being scheduled on some ThreadPool thread, and that ThreadPool thread becomes available, and then it starts executing this operation. There is no thread. And in this case, there is no thread at all. It just creates a task object that doesn't have a thread. Nothing is executing in the background at all. It just creates a new task, and it creates a new timer using timer object of .NET. And it just sets this timer to this value. And whenever timer fires, it transfers the task state from running into completed. This is all it does. So this operation will never use any threads at all. That's why it's so much greater than thread sleep.
Yeah, great. Thank you.
Anyone else? Any questions?
Hello, I have one. Thank you for presentation. Yeah, you show us that in Visual Studio, for example, we have application and we have 4 threads from ThreadPool, yes, and also we have 4 threads, some util threads, as I understand. Yeah, and does it mean that if we have less than 4 cores CPU, it will switch the context every time?
No, if you have a single core CPU, it will only create one thread in ThreadPool. In the old .NET, probably even in .NET Core, just not as recent as 8, because I'm using 8 in this project, ThreadPool created the same amount of threads that are in your CPU core, the logical cores. So whenever you had a 16-core CPU, it would have just created 16 threads at the startup, and it also never removed them. They were always there.
I meant the stopest for threads, which is .NET counterpooler, .NET ThreadPool IO.
These ones.
Yeah. It affect somehow.
They are not used for scheduling your work. So only ThreadPool threads are used to schedule your work. So whenever you use task run, ThreadPool queue user work item, all your delegates will be scheduled on one of these available threads. And in case on one core CPU, there will be only one thread. In case of 2 core CPU, there will be 2 threads. In case of 1 core CPU, if you have 1 thread but you delegated 2 blocking operations, then ThreadPool will create still only 1 thread, but then after half a second delay, it will create you a 2nd thread, and then context switching will start occurring. But until like its limit is amount of cores. These threads are not used for this work that is scheduled by your code. These are just some helper threads that are doing some other different things. I tried investigating because I also wanted to discuss them on these meetups, but I reached the conclusion that they are not important for us. Like this is something .NET related, deep knowledge. So they're not used in this delegation of work.
Cool, thank you.
Yeah, and one more thing I just thought that I will also highlight. So you might think that, all right, I have 16 core machine and it's not so important to not block threads, right? Sometimes I can block some little threads, and if operation is not happening often, then it will be okay. Or maybe even you do not block threads, but you schedule some operations that need to be run concurrently, and you use your number of threads as an indicator. Well, there might be completely different situation on the server side. So, for example, on my pet projects, I use DigitalOcean Droplet, and the machines there have single thread. So I have only one thread to work with. So whenever I need to run something in parallel, context switching always occurs. This is one more thing to think about when designing applications. You need to understand that your application that will be hosted somewhere in Kubernetes, for example, on some cluster, the pods inside that Kubernetes might not have as many cores. They might even have single core, and your application still needs to be responsive. So anyone else has any questions? If no, then I see that we already passed due time. I guess then I'll see you tomorrow on discussion about tasks, and on Wednesday on discussions about async await.
Thank you.
Okay.
Bye.
Thank you.
Bye.
Thank you, bye.
See ya.
Bye.